Okay. Do you see the presentation?
Yes.
Okay. Well, good morning to everyone. My name is Priscilla Rocio, and I'm the last incorporation in Professor Garcia Reyes group. And I'm going to talk to you about a new research line in our lab. This seminar is titled Potential Devices Based on Meta-Organic Frameworks in Combination with Mass Spectrometry Analysis. Current trends in sample preparation within a green analytical chemistry perspective are focused on the minimization of organic solvent consumption, the simplification of the overall procedure, and the use of novel and less toxic materials. Considering this point, miniaturized techniques are a good choice to reach them. Nowadays, the developments in liquid phase microextraction and miniaturized solid phase extraction suppose a challenge in sample preparation field. Maybe miniaturized solid phase extraction present higher interest due to the versatility of the solvent materials employed in its schemes. There are a large number of commercial solvents available. However, a lot of them have disadvantages: low synthetic reproducibility, non-reusable material, and low selectivity. Therefore, it is important to develop new solvent material which present higher extraction efficiency, higher reproducibility, higher sensitivity, and higher robustness. Between these novel materials described in the literature are include mesoporous silica, molecular imprinted polymers, carbonaceous materials, support ionic liquid, inorganic nanomaterials, and metal-organic frameworks. In the last years, metal-organic frameworks, denominated MOFs, have been pointed out as promising solvent materials in analytical chemistry. A MOF is a crystalline extractor based on the coordination chemistry between an inorganic secondary building unit and organic linkers. Under proper conditions, ordered three-dimensional structure with different topologies are obtained. The same secondary building unit can coordinate with different organic ligands. Under specific conditions, the same framework is obtained, but with different characteristics. This is termed isoreticular synthesis. In this slide is shown an example using the same secondary building unit and different organic linkers. The final MOF presents different pore size, different surface area, different gas absorption capacity, but maintaining the same topology. MOF present a variety of interesting properties, and within them could be highlighted that they have the highest surface areas known, they have an excellent chemical and thermal stability, their versatile synthesis, and their pore and cavities are tolerable and can be modified post-synthesis. Due to their characteristic, MOF have been described as solvents in solid phase extraction methods to determine pollutants in different matrices. The potential results are the increase of sensitivity, increase the efficiency, and the reproducibility of the overall procedure. In literature are included several number of miniaturized techniques based on MOF as solid solvent. All them imply the transfer of analyte between a liquid sample and a solid extractant through partition equilibria. The miniaturized solid phase extraction uses a low amount of extractant solvent, always lower than 500 milligrams, and can be divided into two types. The static mode, where the MOF is confined or supported on a device, or non-static, where the MOF solvent is directly added to the liquid sample. This presentation is focused on the devices based on MOF and its use in static approaches. Despite the increasing number of studies with MOF as solvent in different extraction techniques, few authors have paid attention to study the nature of the interaction between the extracting MOF and the contaminants. What type of interaction takes place between MOFs and analytes during the extraction? The straightforward conclusion is that not every moth is able to absorb every analyte, and the extraction efficiency should be evaluated in case-by-case basis. Regarding the most relevant interaction, the pore of the moth in terms of size and shape clearly influencing in the absorption or adsorption during the extraction. But the interaction also depends on the nature of the metal and the ligand. The metal in the moth structure usually behave as Lewis acid due to the presence of insaturated metal sites. Therefore, they can be available for coordination with organic analytes. On the other hand, the organic ligand in the moth structure commonly contains aromatic rings and carboxylate group, able to experience pi-pi interactions or hydrogen bonds with target analyte. In general, the preparation of moths follow conventional crystallization methods, such as evaporization, assisted by microwave, electrochemical deposition, diffusion, chemical vapor deposition, and the most widely used, the solvothermal reaction. Our research group will focus in solvothermal synthesis. During this process, the organic ligand and the metal salts are directly added in a reactor with a proper solvent. After subjected it at high pressure and temperature during few hours, normally this type of reaction are between 2 and 48 hours, a crystalline powder corresponding to a moth is obtained. As a first approximation, two flexible moths are proposed, SIM80 and SIF8. The term of flexible implies some margin of movement in the material structure. In this sense, we have different shapes for the solvent-analyte interaction. In this table are included some physical properties of proposed moth. It is important to highlight the surface areas and the temperature of activation and degradation. The activation temperature is the temperature required. Sorry, what happened? Sorry. Okay, now we are. Sorry, I don't know what I press here. Okay, the activation temperature. The activation temperature is the temperature required to eliminate possible host molecules from moth pores. In this sense, all material surface is able to interact with target analyte during the extraction step. In the slide is show a visual example of activation moth, of activated moth. In this case, is a copper-based moth, the aqueous one, that changed the color from blue to purple after the activation conditions. Here is shown the simulated structure of SIM80 and SIF8 together with their scan electron microscopy image. How to obtain a device based on moth to accomplish extraction techniques and mass spectrometry strategies? Our research group proposed an in situ solvothermal grow using two types of support, stainless steel and nitinol. During these procedures, there are two crucial steps. The first one is the generation of nucleation points onto the support to ensure a stronger linker of moth on the final device. The easier ways to obtain them are subject the fiber to a strong acid treatment with fluoridic acid, piranha solvent, or aqua regia, where the sulfate is directly damaged by the acid, generate some imperfections and ruggedness are generated. The other option is a polymeric treatment, normally with aptes, where the siloxane and long chain favor the moth anchorage. After that, the second step is the moth growth and the proper solvothermal conditions. In the slide, I include a scan electron microscopy image corresponding to a moth coating devices. One of the most extended coating devices based on MOF are fibers for solid phase microstructure schemes that consist in a absorbent material support onto metal wire. Sorry. Sorry. These type of strategies are described in two modes: headspace for the for the analysis of volatile and semi-volatile compound, or direct immersion mode, where the SPME fiber is directly exposed to the sample. These techniques present a large number of advantages, but it's important to highlight the robustness and the reusability of the device. Once the extraction is carried out and the analytes are retained into the MOF solvent, the electric barrier discharge-based ionization can be an excellent strategy to desorb them. In the literature are described the combination of ambient MS and SPME with DART and the electric barrier base, such as low temperature plasma and DVDI. The first approximation we propose is the most widely used in the scientific community, using SPME with other solvent, no MOF. The fiber is directly exposed to plasma for ionization. Several authors use stainless steels as support. Therefore, we must be careful with the distance between the fiber and the MS to avoid secondary current. And to compare the possible effects coming from the supports nature, our research group proposed not only stainless steel wires, but also devices based on methanol, because this alloy has much lower conductivity than the stainless steel. Another configuration proposed the use of coated fiber as grounded electrode in low temperature plasma configuration. A metal support, in this case with main conductive characteristic, is coated with a MOF and use it as electrode. This is the common configuration of fiber coating at the end of the wire. However, we think that the high voltage reach at the end of the fiber can damage the MOF coating and reduce the fiber reusability. Therefore, we propose to coat the support not at the end, but slightly towards the center. The procedure is quite simple. The first step is the extraction in direct immersion on headspace mode, depending on the target analyte. And the second step is replace the LTP grounded electrode by coated fiber based on MOF. In this sense, the analytes are ionized in the same plasma device. Well, until now, the presentation was focused on a wire as a support to obtain a fiber based on MOF. However, the SPME imply other support configurations such as blade. Coating blade are commonly used in 96 well plate SPME approach, where up to 96 samples can be analyzed at the same time. For blade based on MOF, we propose the combination of blade spray and plasma ionization. As the previous extraction proposed, the target analytes are retained into the MOF solvent, but in this procedure, the blade is connected to a voltage to generate a spray. However, probably the ionization is not enough for molecules with certain polarity, therefore use a plasma as secondary ionization could be a good option. In this scheme, we will also study the possibility to increase the desorption and ionization with the addition of organic solvent. The last research line to discuss in this seminar is coated cellulose, to use it as conventional paper spray. Previous strategies of which we have been talking about consist in the immersion of the device in the sample. But what about the deposition of the sample droplet on the device? If we are able to control the growth of MOF in a small area of the paper, few microliter of sample can be deposited on it without losses coming from the paper impregnation. The target compound are retained in the MOF surface area. Then we can use a solvent as cleanup in order to reduce matrix effect. And finally, the blade coating, the paper spray is combining with the plasma to favor the ionization. Geometry can be a crucial parameter in the sortation step. Therefore, we will study different configurations between plasma, device, and MS. And of course, the geometry will be also studied not only in paper spray, but also in the previous configuration with the blade spray. Thank you for your attention.
Thank you very much, Priscilla. I have a question, but any of the audience have any question to ask or to discuss with Priscilla? Now it's time for questions.
Yeah, I had a very quick question. This is Pambos from the University of Cyprus. Why would you consider the dielectric barrier discharge and the LTP for your application? What makes it appropriate for what you're trying to do?
Well, thanks for the question. Our group have searching expertise with LTP and VVI approaches, but in this sense, the first approximation was the use of the fiber coating as electrode. Therefore, it's necessary the electrode and then the grounding electrode, in this case the fiber. And for this reason, we decided to use the LTP. And then I will work with Dr. Bautista, that we'll expose later. And he's now working with VDVI configuration. Therefore, we want to hybrid this to this plasma. So we want to try with this, because in the literature they say that use, for example, the fiber as electrode, but in this way it's not a DVDI configuration, it's more a LTP, just for the theory of the device. I mean.
Okay, thank you.
Agapios, I think Agapios has the no?
Yes, can you hear me?
Yeah.
Okay, so I like the idea of combining the SPME with the plasma source. Since we have a lot of experience with SPME in our lab, okay, the first step is the equilibrium between the material and the headspace.
Yeah.
And then you take the SPME fiber and you just expose it to plasma. I mean, in a normal system, in a normal GCMS system, you need temperature and inert gas to do this. Helium, for example. Do you use any? Okay, the plasma source can give the temperature. What about the inert gas?
But the inert gas, just to make the distortion with the fiber, I mean the plasma device and MS, or use the fiber as electrode, because if you use the fiber as electrode, you have the helium.
No, the first option. The first option.
No, the first option is true. Some authors describe like an inert area where they expose the fiber like a little camera. But in, for example, the last works of Professor Paulison, the expertise in SPME from University of Waterloo, they use directly in ambient without any inert atmosphere. I would like to try how effective is this, because I think the losses can be considerable.
Yes, my concerns are the repeatability of what you are doing.
No. At the beginning, we will start with the same procedure of Professor Paulison that the research group use it directly in atmospheric condition at air without any inert atmosphere.
And what about, you mentioned about the distance, you have problem. How repeatable is this? I mean,
no, yeah, because we if we have the fiber with the stainless steel support so much close to the entrance of the MS, they can experience a little bit of sparkling. And we are afraid about it. Therefore, the two, I mean, regarding the geometry, we have to study not only the position of the plasma regarding the device, but also the distance between the device and the mesh.
If I may ask one more question, what about when you have the fiber exposed in the lab? So the fiber is going to absorb VOCs or any other material that there is in the lab also?
It could be, it's true. But for this reason, it is important to, for example, before the extraction, this is important, the activation temperature. Therefore, if I have my fiber in the lab, there in the storage, we have to activate it at a specific temperature to ensure the pores are completely are completely able to expertise the equilibrium with the target analyte. Therefore, first temperature, activation temperature, then we can make the extraction. And it's true, if we're going to dissolve them in at air, in the ambient atmosphere, it's true, we can expertise some little partition equilibrium, but the desorption would be in seconds. Therefore, I think there will not be a very much problem in this part.
Okay, thank you. Okay. In any case, we have a thermal desorption in our lab. I can show it to Bambos. I think it's an excellent idea to see it if there is this opportunity in the near future. So you're welcome to see this thermal desorption device that is customized by Marx International. In order to help you to what you are doing.
Because it could be a good combination for the desorption. Sure.
Okay, thank you.
Thank you very much.
Agabios, we can shoot a small video and show it to them even at this time. So we can talk afterwards.
Yes, indeed.
Okay.
Okay.